Bismillahirrahmanirrahim. Assalamu alaikum. Our today's topic is about crystallography. Now let's dive in a topic. Symmetry is the consistency, the repetition of something in space and or in time as is shown in the example below. A wall drawing, the petals of flowers, the two sides of a butterfly, the succession of night and day, a piece of music, etc. Petals of flowers having symmetry. According to the type of movement, there are different types of symmetry operations. Number 1. Point symmetry. At least one point is fixed during the movement of the object. Rotation, reflection, inversion, and combination of any above. Number 2 is space symmetry. No points are fixed during the movement of the object. Translation, lattice translation, combination of translation, and any kind of point symmetry operations. Space symmetry operations, glide planes. Glide plane is the symmetry element associated with the combination of a mirror and translation along the mirror. Translation, reflection. Translation, reflection. D is the displacement. A is equal to 2D is a periodicity of a system. Displacement and A is equal to 2D is a periodicity of a system. The displacement within a glide plane is always half the periodicity of the system in the direction of the displacement. Notations of the glide plane. Notation ABC, graphical symbol, dash line or points line. Actual meaning, the glide is along basis vectors A, B or C. G, dash line, the glide is along the line in 2D. N, the glide is along one of the diagonal 1, 1, 0. D, dash arrow, the glide is along the diagonal 1, 1, 1. Reading symmetry diagrams containing glide planes. D, glide direction is parallel to the line for A, B or C planes. D, glide direction is perpendicular to the projection plane for A, B or C planes. And 3, glide direction between the direction 1 and 2 for N planes. Notation for a screw axis. N denotes rotation angle and M denotes the displacement. Alpha is equal to 360 divided by N. D is equal to A into M over N, where A is the lattice period along direction of the axis. 3, 1 plus 2 upon 3 plus 1 upon 3. 3, 2 plus 4 upon 3 is equal to plus 1 upon 3 plus 2 upon 3. Screw axis is the symmetry element associated with the combination of a rotation axis and translation along the axis. Translation, rotation. This screw axis. Translation, rotation. Notation of the screw axis. N denotes rotation angle and M denotes the displacement. Alpha is equal to 360 over N. D is equal to A into M over N, where A is the lattice period along direction of the axis. 4, 1, 0 plus 3 upon 4 plus 1 upon 2 plus 1 upon 4. 4, 2, 0 plus 1 upon 2, 0 plus 1 upon 2. 4, 3 plus 1 upon 4 plus 1 upon 2 plus 3 upon 4. 6 1 0 plus 5 upon 6 plus 4 upon 6 plus 1 upon 2 plus 1 upon 3 and plus 1 upon 6. 6 2 0 plus 2 upon 3 plus 1 upon 3 0 plus 2 upon 3 plus 1 upon 3. 6 4 0 plus 1 upon 3 plus 1 2 upon 3 0 plus 1 upon 3 plus 2 upon 3. 6 3 0 plus 1 upon 2 0 plus 1 upon 2 0 plus 1 upon 2. 6 5 0 plus 1 upon 6 plus 1 upon 3 plus 1 upon 2 plus 2 upon 3 and plus 5 upon 6. Unit cell and atomic positions. Consider a crystal lattice. According to its previous type, we chose the conventional pair triple of basis vector A, B and C. The crystallographic unit cell is defined by putting atoms, molecule, etc. to the sites R1, R2 and Rn so on. Inside the parallelogram based on the vectors A, B and C, the site of each and every atom in the unit cell is given by the fraction atomic positions X, Y and Z. R1, R2 and R3. R is equal to XA plus YB plus ZC with 0 is smaller than X is smaller than 1, 0 is smaller than Y is smaller than 1 and 0 is smaller than Z is smaller than 1. The lattice translations are applied to each atomic positions, that is, if there is an atom with the coordinates X, Y, Z, then there is also an atom with the coordinates X plus U, Y plus V and Z plus W. Translation: UVW is regarded as symmetry operation. Matrix representation of symmetry operation. Any symmetry operation can be presented by the rotation matrix and displacement vector. Suppose the lattice is built on the basis vectors A, B and C and the position of atom are given by the fractional coordinates x, y, z. So that R is equal to xa plus yb plus zc. If we apply the movement related to the particular symmetry operation, the vectors A, B and C are transformed into A dash, B dash and C dash and the origin is displaced by the vector D. The position of symmetry equivalent atom is R dash xa dash plus yb dash plus zc dash plus D x1a plus y1b plus z1c. This rotation matrix and displacement vector. Combination of symmetry operations in terms of matrices. Symmetry operation 1 S1 D1 R1 is equal to S1 R0 plus D1. Symmetry operation 2 S2 D2 R2 is equal to S2 R0 plus D2 and symmetry operation 3 S1 D1 S2 D2. R2 is equal to S2 R1 plus D2 is equal to S2 R S1 R0 plus S2 D1 plus D2. The combination of symmetry operation is represented by the rotation matrix S2 S1 and displacement vector S2 D1 plus D2. For the centered lattice, we know that for 7 out of 14 types of Bravais lattices, the basis vectors are chosen in the way that the unit cell contains additional points. For these cases, the translation by the centering vectors such as 1 upon 2, 1 upon 2 and 1 upon 2 is also a symmetry operation. Forming crystallographic unit cell XYZ, XYZ plus XC, YC, ZC. and xyz plus xc, yc, zc plus uvw. Reducing the position to the crystallographic unit cell, that is providing 0 is smaller than x is smaller than 1, 0 is smaller than y is smaller than 1, and 0 is smaller than z is smaller than 1. Example C, centered lattice 0.5, 0.5, 0. Original position, adding centering vector, lattice vector, the final position in the unit cell. Original position xyz 0, 0, 0, xyz plus rc 0.5, 0.5, 0, and a uvw 0, 0, 0, and xyz plus rc plus a uvw 0.5, 0.5, 0. 0.2, 0.7, 0.7, 0.7, 1.2, 0.7, 0 minus 1, 0, 0.7, 0.2, 0.7, 0.6, 0.4, 0.2, 1.1, 0, 0.9, 0.2, minus 1, 0, 0, 0.1, 0.9, 0.2, 0.7, 0.8, 0.1, 1.2, 1.3 and 0.1, minus 1, 0, 0.2, 0.3, 0.1. Unit cell and point symmetry operations. Suppose that crystal belongs to the rectangular crystal system and has the mirror plane to A, mirror plane parallel to A, then the atom is duplicated by symmetry operation, forming crystallographic unit cell xyz, x minus yz, and x minus yz, x minus yz plus uvw. Reducing the position to the crystallographic unit cell, 0 is smaller than x is smaller than 1, 0 is smaller than y is smaller than 1, and 0 is smaller than z is smaller than 1. Special positions in the unit cell. However, we can consider a special case when the initial position of an atom is the unit cell is x 1 upon 2 z. In this case, forming crystallographic unit cell x 1 upon 2 z, x minus 1 upon 2 z, and x minus 1 upon 2 z, x minus 1 upon 2 z plus 0, 1, 0 is equal to x 1 upon 2 z. Reducing the position to the crystallographic unit cell, 0 is smaller than x is smaller than 1, 0 is smaller than y is smaller than 1, and 0 is smaller than z is smaller than 1. The position of the atom x 1 upon 2 z is special as it is not duplicated by the symmetry operation. Mathematical description of symmetry operations, two-fold axis parallel to C. After the rotation by 180 degree, the basis vector A, B and C are transformed A dash, B dash, and C. A is transformed to A dash, B is transformed to B dash, and C is transformed to C dash. So that A dash is equal to minus A, B dash is equal to minus B, and C dash is equal to C. The position of symmetry equivalent atom is XA dash plus YB dash plus ZC dash is equal to minus XA minus YB plus ZC is equal to XYZ. Two-fold rotation axis parallel to the C provided A and B is perpendicular to C gives two symmetry equivalent atoms XYZ and minus X minus Y Z. Mathematical descriptions of symmetry operations, three-fold axis parallel to C, rhombohedral setting. After the rotation by 120 degree, the basis vector A, B, C are transformed. A is equal to A dash, B, B dash and C, C dash, so that A dash is equal to B, B dash is equal to C and C dash is equal to A. The position of symmetry equivalent atoms should be XA dash plus YB dash plus ZC dash is equal to XB, YC, XB plus YC plus ZA is equal to ZXY. Threefold rotation axis parallel to the 1, 1, 1 gives three symmetry equivalent atoms XYZ, ZXY and YZX. XYZ, ZXY and YZX. Mathematical expressions for the symmetry operation sixfold. Sixfold rotation axis parallel to the C gives six symmetry equivalent atoms minus x minus y z minus y x minus y z x minus y x z x y z y minus x plus y z minus x plus y minus x z. Summary of mathematical representation of symmetry. N. Orientation, the list of atomic position. Twofold, parallel to C, x, y, z and minus x minus y, z. 3. Parallel to A plus B plus C, x, y, z, z, x, y, y, z, x. 4. Parallel to C, x, y, z minus x minus y, z minus y, x, z, y minus x, z. 6. Parallel to C, x, y, z minus x, y, z, x minus y, x, z minus yx minus y, z minus x minus y, z minus x plus y minus x, z minus y minus x, y minus x plus y, z. The reduction to the crystallographic unit cell, that is adding the lattice vector UVW or centering lattice vector, example 1 upon 2, 1 upon 2 and 1 upon 2, should be performed after the above transformation. Mathematical expression for glide plane A. After the reflection in the plane perpendicular to B, the basis vector A, B and C are transformed A, A dash, B, B dash and C, C dash, so that A dash is equal to A, B dash is equal to B and C dash is equal to C. Glide along the A axis displaces the origin by 1 upon 2, 0, 0. Example matrix representation of glide plane. One zero zero, 0 minus 1 0, 0 0 1, 1 upon 2 0 0, S is equal to minus 1 0 0, 0 1 0, 0 0 1, D is equal to 0 1 upon 2 and 0. Thank you very much. Like, share and subscribe my channel Science Kick. Allah Hafiz.